to get more change in magnetic field flux through the coil. Yeah,
Make the magnet out of like neodymium or something.
like a bigger magnet. A bigger magnet, I get more magnetic field, so the change in magnetic field is going to be bigger, right? So I do this. Let's get a bigger magnet. What's the problem with that? Nothing to do with electronics, yeah? Excuse me? Yeah. Well, this is a thin sheet, like a piece of plastic or something stretched, right? And the sound comes, it's supposed to vibrate. And I stick this big clunky magnet on there, that's not going to vibrate. So I can put a brick on it, it doesn't want to move. The sound pressure is not enough to move it back and forth. Matter of fact, any magnet is practically speaking, to get any practical magnet on there, that's a problem. So if putting any practical magnet on there is a problem, you know, some big hunk of iron, even a little hunk of iron. Anybody ever taken you probably haven't taken microphones apart, but you may have taken speakers apart. It's the same basic problem. You know how they solve that? If you have a speaker, you put a big magnet on here, it's hard to get that thing to go back and forth and make sound. Can't get enough force to get enough acceleration. Too much mass. Why don't we flip it around? Why don't we put the magnet why don't we, here's our diaphragm. Why don't we get a really thin wire? We get a really thin wire, and we'll glue on a thin wire with a couple of turns on it. And make the wire thin, it doesn't weigh very much. And over here, we can put as big a magnet as we want, because this one's not moving. So this is fixed. And this is what's going back and forth. So you take the heavy thing and you make it fixed, and what moves back and forth could be a lightweight. So if you actually rip apart a speaker, usually you'll see, at least in this type of speaker, you'll see the coils on the diaphragm, not a magnet on the diaphragm.
But now we don't mention that this was the right?
Any electric guitar players here? A few, sure must have a few. Okay, we got one or two that are embarrassed to admit it. I'll give a homework problem. The electric guitar string vibrates, right? But you need some kind of pickup to generate an electric signal. That's the electric guitar, right? So that's a law of induction thing. We'll talk about that. I'll figure that one out in my homework sometime. Okay, questions on? All right, let me switch to example number 2. So from a historical perspective, this work with electromagnets and these basic laws, the basics were the 1820 to 1830 time frame. In my first lecture, do people remember when I talked about, well, I didn't mention the word electromagnet, but I did talk about how Cornell got started, university. Anybody remember how Cornell University got started? I did mention that, right? How did Ezra Cornell make his fortune? It's a telegraph. You know, telegraph, somebody at one end opens and closes a switch. So you have a battery, some voltage, a battery. There's a switch, and it goes all the way to the, wherever it's going, 10 miles down the road. And over here, there's an electromagnet. And when you open and close the switch, some magnetic field here turns on and off. And if you have some kind of magnetic field detector over here, you can tell that what the person on the other end is doing in terms of on and off. And usually what they did was pretty simple. Usually they would do something like this. They would put a switch here. Let's make it this way. And they would make this, put a little magnet here. And let's see, we'll put a battery here, a second battery. And you could, they had all different kinds of schemes, but let's just put here a speaker. That's AC. Let's just put, let's just keep it simple. Let's just put some little hanging, here's something hanging, and they had a magnet here. They had a hanging magnet. And when the current went through this coil, then this magnet would move back and forth. Or maybe I have to change the orientation, make the magnet like this. But if you put current through loops of wire, we get a magnetic field, and this magnet would move back and forth, and this person 10 miles down the road knows that that switch is being opened and closed. You could put a bell here. When that magnet went one way, it rang a bell. There's all kinds of schemes people use. The basic idea, that was the telegraph. And it depended on having an electromagnet. But the power usually came from a battery here, and that was that. So the next, the telephone came along, as you know. And the telephone basically required speakers and required microphones, and we just described speakers and microphones. And that was maybe 1870 or so. And right around the same time was when electric electric lighting became a big deal. That was in New Jersey. That was Edison. That was the center of it. Those of you who take the train to New York, there's a stop there called Metro Park. That's right where the Edison operation was. And his sort of right-hand advisor, who ran a lot of the company and understood fundamentally what was going on. That was Princeton's first graduate student in engineering, Francis Upton. Anyway, so a light bulb was nothing but a piece of wire that got hot. But they needed some way. They didn't want to. They couldn't back up. It wasn't practical to put a battery in everybody's house because those electric lights took so much power. The batteries that they had at the time would be dead within an hour, and wasn't a practical way to do lighting. So Edison was a smart guy. He wanted to sell light bulbs, so he had to invent a electric power distribution system. Because then people could buy his light bulbs because they way to power it, and that meant you needed an electric generator. Somehow you have to generate something that generates voltages. It's not a battery. So how do you generate electric voltages in a wire? Based on what we just described. Yeah,
move a magnet through the loop of the wire.
right. So suppose I had, I'll just roll one loop, but we know we could have many. And I'll put here a voltmeter, plus and minus. And I'm gonna have a magnet here. And I move it this way and I move it that way. And I keep going back and forth. If I look at the voltage here, it's going to go up and down. So this is the basis. This is the physical basis for all electric power generation. I don't use the word all, someone will find some strange except, it's not solar cells, classical electrical power generator. There's a loop of wire, or probably a coil, as we know, and someone is moving that magnet back and forth. And it's mechanical work to move that magnet back and forth. So that means we're translating mechanical energy goes to electrical energy. How do you use this to light a customer's light bulb? This is in Edison's generating station. He's got some machine making the magnet go back and forth. And he's got loops of wire, and he's got some voltage here. We can put a voltmeter on it. The customer is over here. So what will happen is the two wires will go over to the customer's house, and we'll put a resistor here. So here's the customer. We'll put a resistor here. We know there's a voltage between these two wires. What happens in a resistor? There's current. Right? So there's current flowing here, depending on whether on the top or the bottom of the cycle the current is going up and down. What happens to the resistor? It gets hot. It gets hot enough, it glows white hot, and that's a light bulb. So, this idea here of moving a magnet closer and farther from a loop of wire, so that's the basis for power generating stations. It could be coal, could be oil, could be gas, could be nuclear. It's all the same thing. Yes?
So I'm trying to think of how the light bulb wouldn't flicker because, well, because the magnetic field is changing, but is it?
That's right, because the voltage goes up to 0, to negative to 0, right. Yeah, so the question is how fast do you have to, if you did it once a minute, it would clearly be too slow. But if you did it 60 times a second, probably wouldn't notice it. Yeah, so the US is based on 60 hertz. Anybody here from Europe? Not one per one. What's the frequency of electricity over there? You never took an oscilloscope and tested it? 50 hertz. Well, so the world is divided between 50 hertz and 60 hertz. So for a practical point of view, as far as light bulbs go, it doesn't matter. Good question. Yep. Okay. Yeah, so that's an electric generator. You ask, well, what does the oil or the gas or the coal do? Any idea how that figures into this? Well, all the oil, the gas, or the coal, or the nuclear energy for that matter, all they do is boil water. All they do is boil water. And then they picked up boiling water and they connected it up to a giant heat pipe. And you have a stream of steam coming out. And so in my electrical engineering view of a mechanical system,